All right, hi everybody. We're ready to begin the second talk of our afternoon session, and we're glad to. And this will be the first talk by a speaker from the conference venue in Lisbon. So Pedro Aniceto is going to be talking to us about R-square corrected ADS2 holography. Over to you, Pedro.
Hi everyone. First of all, thank you, Gabriel and Suresh, for organizing this very nice workshop that has to be done online, regrettably. So today I'll be discussing with you a model of ADS2 holography where we are considering a theory of gravity with R-square corrections. This is based on ongoing work with Gabriel and Suresh. Oops. Okay. I will start by giving you the main motivation for the work that we have been developing, and presenting you the theory that we'll be studying. Then I will go on with the discussion of how to proceed with reducing this theory to, in our case, 2 dimensions, and then create a well-defined variational principle for it, and then proceed with its holographic renormalization. Afterwards, I will be discussing the asymptotic symmetries of the theory, and with it, I'll try to address what kind of physical information we can actually obtain from the theory. And then I'll finish with some conclusions and mention some future work that would be interesting to pursue. So let's start. The main goal will be to determine the holographic dual of a specific subset of 4 derivative n equals 2 low energy effective actions of gravity in 4 dimensions. This 4 derivative appears specifically in R-square corrected terms of the theory. And what motivated us to search this was actually trying to use the holographic principle to capture information about the entropy of the 4-dimensional black holes by studying it once we have reduced it to 2 dimensions. For that, of course, our end goal will always end up being studying ADS2 CFT1, and we'll be focusing at the end of the day, we will be, of course, focusing on extremostatic near horizon backgrounds, because these are the ones that would factorize into ADS2 times S2. So the theory, sorry, before that, ADS2 holography has certain difficulties associated with its description. Chief among them towards our work has to do with the fact that pure ADS2 gravity does not allow finite energy excitations. One way to circumvent this problem is actually using the NADS2 and CFT1 correspondence, and in which one would break the conformal symmetry of the theory by taking a non-trivial profile for the scalar fields coupled to it. This is not what we are going to do. We are actually going to focus on ADS2 for where we take the scalar fields to be constant. The dictionary for this was described, for example, in this paper from 2016. And the main characteristics of the dictionary in this situation is that the holographic stress energy tensor will vanish identically. And so we are always at the ground state of the theory. Nonetheless, there's some non-triviality related to the dual operators to the constant scalar fields, which even though they are irrelevant operators, they will find that they encode some information about our theory in them, and that they transform in an anomalous way under the asymptotic symmetries. And this leads one to postulate that perhaps there's a way to account for the microstates of the black hole entropy to survive and in this ADS2 constant scalar field situation, and to be given by the expectation value of the 1-point functions associated to these dual operators. So we are focusing on a 4 derivative n equals 2 low energy effective actions that are we use them in 4 dimensions, and they are obtained from Calabi-Yau threefold compactifications of superstring theory. They are described, for example, in this paper. And in terms of field content, what we are discussing is gravity coupled to a billion gauge fields and constant scalars, or scalar fields more accurately, not necessarily constant. And this coupling is encoded on the usage of a holomorphic function that has a certain particularity about it, which is that it is a homogeneous function of second degree. At the end of the day, we'll be, of course, focusing on extremostatic near horizon backgrounds, and moreover, on BPS configurations, so that we can actually use the tractor mechanism to, which will allow us to simplify water computations. So let's start discussing how we actually obtain the two-dimensional effective action. So we have a four-dimensional metric that we decompose in this manner that you can see here. We'll consider the metric in 2 dimensions given by the Hij, and we see here the factor coupled to the S2 as the dilaton. This V2 will be called, for most of the talk, the dilaton. We will also relate it sometimes with an exponential of psi, and this is the relation, but you don't need to memorize it. I will present it whenever it's necessary. Just take into account that B square will be a scale that we use to relate the two-dimensional Newton's constant with the four-dimensional one. As I had mentioned already, the four-dimensional theory is supported by it's coupled to a billion gauge fields. These ones have electric fields EI and magnetic charges PI. And of course, we also have the constant scalar fields. These are given by the x's within the index I, and this A hat, which if you are interested in knowing, it's basically the squared of the graviphoton field strength. And of course, I had already mentioned before the homomorphic function f, which will depend on the scalar fields. We furthermore set the four-dimensional Newton's constant to be given by this combination of the scalar fields with the homomorphic function. In terms of notation, these indices, whenever we appear the homomorphic f with these indices I or A or epsilon eventually, it just means that it's a derivative with respect to them. So under this ansatz for the metric, our four-dimensional Ricci scalar will then decompose into into the curvature of the two-sphere. Note here that we are not using the most frequent, I'd say, definition for the Ricci tensor. So the two-sphere has negative curvature in our nomenclature, and the ADS will be positive in that case. And yeah, eventually we'll be interested in the ADS2 solutions, and written in the Pfefferman-Graham gauge. This can be solved, and their general solution can be written locally under this form. So using all of these ansatz, we reduce our Lagrangian from 4 dimensions, and in 2 dimensions we obtained this not terribly enlightening expression. What you should take in mind when looking at it is, first of all, we have already redefined the scalar fields. We now use, and will use for the rest of this talk, yi and epsilon. Here, I would like to point out that the yi is linear in the dilaton and the epsilon is quadratic in the dilaton. This will come into effect later on. So this not so nice Lagrangian, you can see here the electric fields. Just to remind you, these are the electric fields, metric, dilaton, magnetic charges, second derivatives of the homomorphic function f. We have the standard Riemann-Hilbert term here. Recall that this was our definition of the four-dimensional Newton's constant, and we also have some terms that are linear, that are just depending on the scalar fields, and a polynomial in the curvature. Furthermore,
sorry, can I ask very, very quickly, are you assuming that V2 is constant?
Yes, yes, yes. We are assuming everywhere that V2 is constant. We will, since we are not doing NADS2, we will not introduce dynamics to it. So we did not take its derivatives into account when reducing to 2 dimensions.
Okay, thanks.
No problem. Where was I? Okay. Yeah. So we'll actually not use this Lagrangian yet. We'll take first a Legendre transformation with respect to the magnetic charge, so that we can make electric-magnetic duality evident, and this H is now the Lagrangian that we'll be using henceforth. Here, the things you should retain are that we have a term that is quadratic in the electric and magnetic field, a term that is linear in the electric and magnetic field, a very bad notation where we use f of r, which has nothing to do with the holomorphic function f. Whenever I say f of r, I mean a polynomial in R that is given by this expression here. And when I say holomorphic function f or function f, I mean the holomorphic function always. And yeah, some terms that depend on the scalar fields only. For the polynomial in R, I would, so we have here the Riemann-Hilbert term, and the extra terms that come from the R squared corrected terms. Things to point out here. First, how f encodes this, how the holomorphic function f encodes these R squared terms. When we don't consider R square interactions, we assume that the holomorphic function f doesn't depend on epsilon, but giving it in the dependency on epsilon allows us to then see the R squared terms in this manner. Here, also considering that there's a denominator with V2 in it, we see that there is a term that is linear in V2 in this whole expression here. And there's a term that this V2 cancels, so it's linear in the square root of minus epsilon. This will appear because of, I'm just mentioning it because it will appear again in the variational principle for the boundary contour terms. So let's start discussing the variational principle of our theory. We have some dynamical fields. These are the metric, the gauge fields, such that their exterior derivatives give us the magnetic and electric fields, and the scalar fields, which are the yi, the epsilon, and the v2. And what we are going to do now is to add counter terms to our two-dimensional Lagrangian to impose Dirichlet boundary conditions at the boundary at infinity. And also we'll have to take some care in treating the gauge fields and renormalizing them so that they preserve the symplectic structure. This is a procedure that was mainly based on the description of this paper from 2010 from Papadimitriou, and it's a procedure that has already been used quite a lot in the literature. Like in these 3 papers, it's very nicely described how to do it. In terms of preserving the symplectic structure, what do we mean by that? So basically, we are imposing that our boundary counter terms have to be compatible with the symplectic structure on the space of asymptotic solutions, but that they also somehow preserve the gauge symmetries of our symplectic variables. And this means that they will end up generating a canonical transformation that I will show you in a minute, which diagonalizes the symplectic map between the phase space of our theory and the space and the symplectic space of asymptotic solutions. So let us see what the problem is and how to deal with it. Sorry, yes. Here you go.
I was confused by the presence of square roots of this epsilon.
Analytic
epsilon goes to 0, the effect of the scaling.
The epsilon doesn't go to 0. The epsilon is a constant real value, has the constant real value of -64. So yeah, at the attractor point. I will show you afterwards when I will show you the solutions to the equations of motion. So on shell, the square root of minus epsilon is just number 8.
Sorry, if I may comment on that. Epsilon is the rescaled graviphoton field, and after the rescaling becomes a real field. Okay.
where was I? Oh, okay. So for the gauge fields, we are taking a gauge in which the radial component is 0. And if one were to solve the equations of motion, we would find this general expression for them, where we should have in mind that the term that dominates, because of the fact that the electric fields are proportional to the square root of the metric, the term that dominates, and this is an issue in general for ADS2 whenever we are working in ADS2, is that the term that dominates is the mode that is related to the metric. This is meaning this is a divergent mode. And we see that at the boundary, this washes away the chemical potentials of the gauge fields. So if we were to just proceed without renormalizing them, the symplectic map would then not be able to diagonalize, because we would have mixtures of alpha and conserved charges that appear also here. And the conserved charges would also appear in the renormalized canonical momenta. And so the symplectic map would not be diagonalized. So the way to proceed is to then add at the boundary counter terms that indicate that you are doing a Legendre transform. You do this first one makes it so that you are actually varying the canonical momenta, and you then add a boundary counter term that depends on the canonical momenta, so that the gauge fields end up being renormalized. So these two terms in red end up giving you this canonical transformation on the fields. So you see, we keep the conserved charges constant. They are not disturbed in any way, but we end up renormalizing the gauge fields, and the whole idea is to find the boundary counter term that kills off this alpha leading term in the gauge fields. In the end, we use another Legendre transform already. This is unlike these terms that are divergent on shell. This term is completely finite on shell. It's completely well behaved, and we just add it to the action so that we impose Dirichlet boundary conditions on the chemical potentials and not on the conserved charges. So this is the complicated part of the variational principle. On the other hand, we also have to deal with the f of r term. Oops. For the f of r term, we deal with it in the usual manner, adding the Gibbons-Hawking-York counter term. We have to determine the induced metric, and it's very easily computed. And notice once again the not so usual sign here. It's because of our definition for the Ricci tensor. And we have to add a second counter term that we take it to be 0 on shell. That has to do with what happens when we vary the Gibbons-Hawking counter term when we have a polynomial in R. Meaning, so if we were to vary this term, there would still be a dependency on R that would give you a delta R, and we kill it off by adding this specific term. So all in all, the boundary counter terms for our action that are necessary to define a well-defined variational principle are this whole expression here, where I am omitting the Legendre transforms that I mentioned for the gauge fields. So just to recap, we have the Gibbons-Hawking counter term. We have the second term that is 0 on shell. The S of prime terms are given by these two counter terms here. You can see that they depend on the canonical momentum. There's a term that is quadratic in the canonical momentum and a term that is linear in the canonical momentum. Furthermore, we have another term that on shell by itself it's also 0, as we'll see in the slide after this one. And if you look at the way that this term behaves and the way this term behaves, you'll see that they capture exactly the linearity in V2 times R and the linearity in the square root of minus epsilon that was appearing in our action from the get-go. And also this minus 8 term cancels with this minus 2 term. So these two extra terms, sorry?
So I have a question, Samir.
Yes.
At the end of the day, the equation of motion has two derivatives or more?
At the end of the day, the equations of motion will end up having only two derivatives, yeah. So,
So the higher derivatives do not appear. The boundary terms are such that they don't appear.
yeah. They appear for the well-defined variational principle, because it's the variational principle is done off shell, and then it will be evaluated on shell for the renormalized action.
Sorry, so I didn't understand the answer at the end. So the equation of motion that you get from this variational principle has how many derivatives in time?
In time, it has at most 2 derivatives in time, because we are imposing the constant scalars.
So you've managed to kill the higher derivatives coming from this R square term.
You don't manage to kill they.
I think he's just assuming that the background is ADS2 times S2. So the higher
Exactly.
derivative terms are just going to influence the attractor values of the radii, right?
Exactly.
I see. So there's no dynamical graviton.
Yeah, that's the case indeed.
I see. Okay, thanks.
So yeah, this is not the same. The solution to the equations of motion is not the same as you would obtain only considering these equations without R-square corrections. And where was I? So yeah, these extra terms of course then have to be done so that the variation of the scalar fields are also finite, and they are such that the sum of these 3 terms here plus these 2 terms is also 0 on shell. So on shell, when you evaluate them, only this term here will be non-zero, and also the Legendre transform terms. So the solutions to the equations of motion will give you that V1, so the RADS scale is equal to the dilaton, squared is equal to the dilaton. Recall that we were using in the Pfefferman-Graham gauge, the solution we were giving it in terms of these modes. And yeah, under the attractor equations, we find that the scalar fields depend, as they should, on the charges of the black hole. And the epsilon indeed ends up with this numerical factor only. And on shell, we find this value for the Newton's four-dimensional constant. And yeah, I had also mentioned before, but I hadn't given it the solutions to the equations of motion for the electric and magnetic fields, but they are given by these expressions that, as you can see, are proportional to the square root of the metric, as I had mentioned before. So having defined our variational principle, we can then proceed with its holographic renormalization. We have a renormalized action that we'll be evaluating on shell. We vary it with respect to the fields, and we consider the asymptotics on the asymptotic space of solutions, variations of this sort. Just so I'm clear, here, supposedly I should also be taking the variations with respect to the other scalar fields. I just omitted them in this slide because I will not be taking for now sources to these fields. So the modes that the Pfefferman-Graham gauge modes that were parameterizing these solutions, the leading ones at the boundary are given by these expressions that are the ones being varied. You see here the chemical potentials, which is what we expected to obtain, of course. And we also will add a source new that will be due to the irrelevant operator that will be sourcing the irrelevant operator that is due to the dilaton, where of course you should recall now that since the other scalar fields were also depending on the dilaton, they also will end up giving contributions to this pi of V2 renormalized. So substituting in this expression the variations, we end up obtaining the variation of the renormalized action in terms of the sources, and this allows us to define the one point functions of functions of the dual operators to the sources minus alpha square, mu I, tilde mu I, and nu. And they quite straightforwardly are given by these expressions, which when evaluated on shell show us that, as expected, the holographic stress energy tensor vanishes identically. This was to be expected since we are not considering any kind of perturbation, as we will see in a bit. For the canonical normalized moment of the gauge fields, we find that they are proportional to the charges, as also we expected, and an expected factor appears in the pi of V2, which is non-zero because of the source we considered. We obtain a finite term that depends on the subleading mode of the metric. If you recall, beta was the subleading mode of the metric. And I just would like to remind you that the four-dimensional Newton's constant still has this expression here. And so the renormalized action can also be written in terms of the sources, and it's just given by this very simple expression, where you should note that we will be always working at zero order of nu. So that's why I'm not really worrying about the back reaction effects. So I'm just really using it to generate the dual momenta, the dual operator to V2. Some key takeaways here are that this prescription that we just used would have been equivalent to using just the scalar fields as V2, Xi, and A hat, and sourcing only the V2 again. This is similar to the result obtained in the Sept Papadimitriou paper. Of course, they were considering a different theory, so it's not the same theory. And you should also notice that the functional form of the result does not actually depend on R-square corrections, in the sense that this functional form would be exactly the same if we had not considered the R-square corrections, because the term appearing here would be exactly this one. Nonetheless, the R-square corrections are encoded in our homomorphic function f, since now it depends on epsilon, and of course there is a different value just because of it. So having defined our renormalized theory, assuming these sources, we will proceed with discussing how these different operators transform. And in particular, we will be analyzing the scalar operator, since it's the one that I had mentioned before was the one inducing the non-triviality of the theory. For that, I will need to discuss the asymptotic symmetries of the theory. I'll start by discussing how we obtain them. So we are working in the Pfefferman-Graham gauge, and we are also imposing that the radial component of our gauge fields is 0. And we still have some residual gauge symmetries in this case. They are given by the Penrose-Brown-Eno diffeomorphisms together with some composite gauge, some gauge transformations. And they are computed by solving these differential equations. And the solution that we present here using exactly the same notation as the 2016 paper is written in terms of 4 parameters: epsilon, which is clear from this description, generates the boundary diffeomorphisms; sigma, which generates Weyl transformations at the boundary; and the phi's that generate the gauge symmetries of the chemical potentials. On the sources, when applying these residual gauge symmetries on the sources, we find that they act on them like this. And since we are working at 0 order on the new source, we will not be imposing anything on it. But we will be imposing that for our symptotic symmetries that they leave the sources invariant. And so we have 3 differential equations to solve, and they can be solved in general by this form, where the zeta is just a function of t that we wrote it like this just because it simplifies the notation that we'll use afterwards to discuss anomalous transformations, and the ki's, which are just constants of integration, as can be seen immediately from the form of the variation of the mu's. So plugging this subset of symmetries into the transformations of the gauge fields of the Pfefferman-Graham modes, we find defining a new time coordinate based on the square root of the renormalized metric at the boundary. We find that they can be rewritten in this form, and that the beta mode transforms with an anomalous term. And this, of course, implies immediately that when we check the asymptotic transformation of the one-point function of the dual operator to the dilaton, that it also transforms anomalously. The first term, so it looks like it transforms like to tensor together with an anomalous term. And this anomalous term has a central charge that is up to a numerical factor given by a quadratic term in the sources over a scale. This was actually our main motivation initially for looking at this holography dictionary with R-square corrections, because when you don't have any kind of R-square correction, what you would be finding in most of the theories that were studied was that this central charge seemed to be proportional to the central charge of the dilaton, of the operator dual to the dilaton, seemed to be proportional to the entropy of the black hole. In our case, you see that if you had not considered R-square corrections, this would indeed be the case. You would have found that result. But when you consider R-square corrections, indeed, this is no longer the case. So we have not captured in any way the entropy of our four-dimensional black holes with this central charge. And I would just like to also point out that this is a result that is also very reminiscent of previous results that were discussed for in theories of in two-dimensional holography discussions, namely in this paper from 2008, where they considered a different variational principle, and the central charge in that case, instead of being for the dual operator to the dilaton, was actually for the renormalized holographic stress energy tensor, but it was also of this form, and it also made contact with some bulk calculations that were done by considering ADS2 as a CFT2 and seeing how inducing a central charge by considering a warped stress energy tensor with where one considers that the conserved current, the gauge field conserved current transforms in a non-gauge invariant way. But yeah. So looking for a way to actually capture the entropy of our four-dimensional black holes, we were led to rethink about what kind of scalar field could we be considering and what kind of scalar field could we source. And what then came to mind was look at our homomorphic function f. It's as I said before, it is homogeneous of second degree. This is what we mean by homogeneous of second degree, this expression here. Also notice how just because it will be useful, and I guess you all might already be tired of seeing it, but just to remember you all the time, that the Newton's constant is homomorphic of first degree under these changes in lambda and lambda square for the epsilon, as can be seen because this term is of first degree, this term is of first degree. This is a derivative of a second degree by a first degree term, so it's also first degree, so it ends up being of first degree. Anyway, so we consider a composite scalar field whose asymptotic variation is written, once again, it would be sourcing an irrelevant operator, and its composite and its variation is given in terms of of the following vector field that we build, so that it basically gives you the eigenvalue of the homogeneity of the functions you're considering. So you can see here that it basically gives you a 2 for the homomorphic function f, and it also acts on the Newton's constant as follows. So varying the renormalized action with respect to this composite scalar field, we obtain this expression that's once again rewritten in terms of the sources, can be presented in this manner. The procedure is still the standard one. So we want to renormalize your, this is just the renormalized variation of the scalar y field, and this is the normalized variation of the epsilon field. And now cheating a little bit, remembering how the f of r term goes, like its first derivative is given in this form, where we notice that this component here is homogeneous of degree 1. This component is of degree 0. This two also of degree 0, and this one is of degree 1. So acting on this with the vector field that we had defined before, the only term that this term stays unchanged, and this term is the only one that survives. However, on shell, you should also note that these two terms cancel each other. So on shell, this term is also the only one that survives. So we find that when we act with the vector field on the f of prime term, we keep it fixed on shell. So we end up finding a new irrelevant dual operator, or the fixed point for the irrelevant dual operator. And it also will transform anomalously due to the beta term that it has. And just to keep it simple, the anomalous transformation, we can set alpha to 1 and beta to 0. This would be the extremal black hole case. And we see that it has a central charge that is proportional to f prime of r. And if you were to compare this with the 4-dimensional black BPS entropy of our solutions, you would find that this is indeed the value. This can be obtained either using Wald's prescription or using the entropy function formalism. So we can indeed build a scalar field in our theory that would capture the information of the 4-dimensional entropy. However, at this point, we don't know how to motivate its existence or show what scalar field it is.
Sorry, can you flash again what the definition of the pi hat was?
The big one?
Yeah.
It's the sum of these two.
Oh, it's that thing. Okay. Oof. Okay. Thanks.
So you see that there's an extra r other than the one of the renormalized metric. But yeah. So it's also an irrelevant operator, but yeah. Finally, one thing that one can actually discuss using these theories is compare them with the ADS3 description that one can obtain when one lifts these theories to 5 dimensions. So our 4-dimensional solutions under specific impositions, namely, you should take one of the abelian gauge fields and set its magnetic charge to 0. And then you can treat that gauge field as a Kaluza-Klein vector field. And with it, you can lift your solution to 5 dimension, and you will end up with 5-dimensional n equals to supergravity with r squared terms that admits black hole solutions that will factorize into ADS3 times S2. And so you can actually study how that ADS3 behaves, and this was done already in this paper from 2007. And so what I'll do for the next few slides is to basically rewrite our theory in terms of the second and of the 2-dimensional Newton's constant. And this is done so that we can adapt our results to the results of the Sept and Papanimitriou paper from 2016. And because we can then use their lift to 3 dimensions to compare our results in ADS2 with the results of ADS3 that were done in the paper of Castro et al. In 2007. So the whole idea is to, as I had introduced before, just redefine your fields to make the dilaton evident everywhere. And you also will need to redefine your 2-dimensional metric in a way, specifically the modes of the metric. Once again, you end up obtaining using all of the previous procedure to obtain the dual operators through holographic renormalization. You end up obtaining this 1-point function that we have here that will, as before, transform anomalously. You have to actually also be careful in be careful in defining your syntactic symmetries, because some factors, of course, would be off if you just repeated the equations that I gave you above. On the other hand, you compare this with the 5-dimensional point of view, where the ansatz for the lift is given by this metric here. See, we consider the gauge field to be A0, the one with without a magnetic charge. And in 4 dimensions, we consider a specific homomorphic function f that is given in terms of 2 constants CABC and the C2A that are associated with the Calabi-Yau threefold data. Given this homomorphic function f, we can solve the equations of motion, the trajectory equations, and obtain results for our scalar fields. And with them, rewrite the dilaton and so on, and rewriting them in terms of the 5-dimensional theory terms, in which the only thing to mention here is that I'm just considering a short notation where the dot is just basically contracting all indices together. And so doing all of this, we end up obtaining the following value for the dilaton in 2 dimensions, and we can then rewrite the 2-dimensional CFT stress energy tensor, meaning the 2-dimensional CFT that comes from ADS3 in terms of the anomalous operator that we had obtained for the dilaton. This is just using the results of the 2016 paper. And so, yeah, as I had said before, it transforms anomalously, and it transforms, and the anomalous term is given by this C over 24 pi given by the 3-dimensional Newton's constant, which in our case is just the period of the Kaluza-Quine circle reduction and times the 2-dimensional Newton's constant. And when we then write this all together, we end up finding this expression for our central charge for the anomalous operator, and this can be seen then to have exactly this relation with the right moving central charge of ADS3. So C is our C for the anomalous operator of psi. So yeah, I'm just mentioning this because, as you can see, even though we have an irrelevant operator in 2 dimensions that is basically being suppressed in the infrared, it still captures information about the relevant physical information that one would have found from the reduction of ADS3 to ADS2. So, having said all of this, I would just like to conclude what we have done here. So, we have obtained the renormalized variational principle for this theory for constant scalar fields. We have identified the expectation value of certain irrelevant operators due to the scalar fields of the theory. Using our syntactic symmetries, we found that we can basically describe a composite operator that depends on a vector field, that you can obtain this operator by integrating the vector field. And you find that its central charge is proportional to the 4-dimensional black hole entropy. And we also shown that under a lift of ADS2 to ADS3, we see that the ADS3 information is captured in the anomalous transformations of some of the fields of our theory in 2 dimensions. This is once more a hint that at least in the situations where you can actually go from ADS3 to ADS2, that the holographic dual of 2-dimensional quantum gravity might encode data that is embedded in the chiral half of a 2-dimensional CFT. While when going from ADS3 to ADS2, this is something that can always be done. Not all of our solutions, of course, admit an ADS3 lift, so we don't have any way of specifying what the 2-dimensional CFT would be in any case. So what would be interesting to do then? well, the main thing would be to introduce dynamics by basically perturbing away from the infrared fixed point. And this would introduce several difficulties. The main ones would be that we have quite some scalar fields that would need to be back reacted in that case. And there's a lot of kinetic terms for the dilaton that cannot just be ignored. Namely, we would have second derivatives and fourth order derivatives of the dilaton appearing, and that would then need to be integrated at least perturbatively. One way that we're thinking of proceeding with this would be to give that back reaction, but constraining it so that our four-dimensional Newton's constant would be fixed. So this would imply, for example, that we could give a source to epsilon and V2, but it would have to imply that the yi's in that case would not be back reacted, for example. On the other hand, it would also be interesting to further explore the possibility of the CFT1 in ADS2 CFT1 being given as a chiral half of a certain two-dimensional conformal field theory. This was already something that was a kind of motivation for the Hartmann and Strominger paper from 2009. And it's also something that appears a lot in the literature. I'd say, I think recently it was also shown in 3 dimensions in this paper that for topological massive gravity, this is also happening, that the infrared dynamics are capturing one of the chiral halves of the 3-dimensional theory. So I'll finish here. Thank you for your attention.
Thanks a lot, Pedro. Okay, questions, comments?
Let's see, I have a question. Oh, this is super nice. I was curious, so in this case where you had, when you were doing the comparison in 5D, as you reminded us, you have this P right and this P left. From your analysis, there's no evidence or lingering of the P left, right? Everything that, like all the observables that you computed dependent only on piece of the right moving part, right? You're muted, so I can't hear you. Pedro, you're muted.
Sorry. Yeah, we only found the only observable that we were using to compare was the central charge, and yeah, we couldn't find any evidence of the other term, the C left in this case. Yes. Yeah,
I see. Yeah, I've been a bit frustrated about that, of trying to find something that depended on the left moving thing.
But yeah, like we also used the prescription that was bound to not find both of them, because the lift itself would always be forcing us to only capture one of them, because if I recall correctly, when we use this lift here, the other component of the stress energy tensor in 3 dimensions will be trivial with the data that we have from the 2 dimensions.
Yeah. And then I guess the other question I had, maybe, I guess the way you're doing this treatment is also very natural to compare with Ashok-sen's like quantum entropy function, right? And so you find agreement, nothing strange being, because he also does like a holographic renormalization of ADS2 and in perhaps slightly different language, but I guess it's compatible with his picture.
As far as I'm aware, I think Gabriel could detail it a bit more, perhaps. But yeah, we were also looking at trying to find some kind of holographic entanglement thing, but we couldn't find anything. And yeah, it's also
okay.
That was also something that he was looking for, I'd say. But yeah.
Thanks.
You're welcome.
Okay, so if there are no other questions, let's thank Pedro again. All right, and that's it for today. We'll reconvene at 9 a.m. Lisbon tomorrow. Thanks to all the speakers. Thank you.